mercury is easily accessible. Everywhere you can procure mercury in the remotest area of Africa, for example. It's easy to use. You don't need any training. Just mix and you get some gold, and it's very cheap. Even with the Minamata Convention that hopes will have an impact on the price of mercury, mercury will still be a cheap product compared to the gold that is extracted. Second point is that it provides gold daily, which is an important aspect for rural poor communities that need a daily income. So by using mercury, you get a daily income. The miners, of course, are not aware of the risk, and therefore they tend to overuse mercury and to pollute their own environment without any idea of the impact it has in the long term on their own health and the health of their children. And they, most importantly, they believe it's efficient, where in fact, in terms of mineral extraction, mercury is not an efficient way to extract gold. It's cheap, accessible, and easy to use, correct, but there's much better ways to extract gold. And the major barrier for miners is their informality. Miners are not formalized, and therefore they cannot either obtain the investment needed to move away from mercury, and they can't invest in large piece of equipment because they might have to run from one day to the next out of their mining site. To give a overview, so this is the latest figure from the Global Mercury Assessment of UNEP that was published in 2013. The new edition will be available this year, and it shows that mercury from artisanal and small-scale gold mining is in fact the largest emitter of mercury to the environment. And by emission here we understand atmospheric emissions. The emissions to the water and to soils are not taken into account. Of course, if we do take this into account, the proportion is even greater. We're going to go through the typical process of the gold extraction by artisanal and small-scale gold miners, and I'm going to point out where mercury is used and what can be improved in the process. So the extraction of the ore, here I have two examples of typical working sites. Some sites use timbering to protect the workers. Some sites don't do at all. There's areas in the world where miners don't remove water from pits so that they don't collapse and therefore dive to recover the gold. Crushing and grinding, in most cases it's done artisanally. In these pictures you can see that the crushing is done by hand on the picture on the left, and you can imagine that the level of accuracy and the level of quality of the ground material is therefore very limited. On the picture on the right, this is what you observe a lot in I got sorry, there was a problem with the mute function. I hope you will hear me. The miners use actually flour mills to ground the ore, and creates a lot of problems for health. As you can see, there's a lot of smoke, and therefore create other type of exposures through silicosis, for example. And this is not automatically, as we will see later, a best way to obtain gold liberation. In the next slides, we have the step of concentration. Once the miners have extracted the ore, and then grounded to supposedly liberate the gold. Some of them, and it's not used everywhere, that's why I put this mention, concentrate what they have ground so that the gold can be better extracted. This is actually a best practice. It's necessary to concentrate the ore because the gold in the rocks or the deposits is usually 10 to 15 grams per ton. And therefore, in order to be able to process further, it's important to be able to concentrate your product. This is possible because gold is heavier than the minerals it is surrounded with. And therefore, if the grinding and the crushing has been done properly, the concentration process can be very efficient. And it can be mechanized or not. Some miners use manual concentration. Some miners use sluice boxes as shown in the picture. Then miners use amalgamation to recover gold. Sometimes it's done while grinding, and that is a worst practice. The Minamata Convention on Mercury identified 4 worst practices that needs to be banned. One of them is the use of mercury while the miners are grinding, because this process uses a lot more mercury that's needed. This process renders the process very inefficient, and therefore a lot of losses are produced. Instead, miners should concentrate first if they want to use amalgamation, so that a minimum amount of mercury is used to recover gold. That's what I mentioned here, the hollow or amalgamation. So the amalgamation without pre-concentration is a banned practice under the Minamata Convention. This practice can lead to releases of mercury of up to 40 times the amount of gold produced. So this is where the bulk of the emissions occur, of the releases to the environment, I should say. Then miners roast the obtained amalgam, often in the open, as we can see on these pictures. Some of them tend to know about the risk, like this miner on the left picture that tries to protect himself from the fumes, ineffectively, I should say. And some are totally unaware of the risk, like the family on the top left, right corner, that really is all around the happening of the roasting, so that they can't see the gold being produced. This is a huge issue, and actually these are 2 of the 4 worst practices that are identified in the Minamata Convention, and that have to be banned. The first one, miners cannot roast in residential areas. They have to, if they use mercury, they have to do it in the working place, away from where they live, and they cannot roast in the open, meaning that they have to use mechanisms or capture tools that will capture most of the mercury fumes and will not lead to emissions of mercury to the environment. This is where we have mercury emissions, and typically if the amalgamation has been done well, and that there is not too much other metals than gold in the ore, here the emissions factor is 1 gram of mercury emitted for 1 gram of gold produced. And the last point, sometimes miners, and it's more and more common in some parts of the world, because they know that mercury amalgamation, the way they employ it is not so efficient, decide to go further and use chemical leaching using cyanide. This is, again, a worst practice. This is the last of the worst practice of the Minamata Convention. Miners can elect to use non-mercury technique, they can elect to use mercury techniques, and they can elect to use chemical extraction. But if they do use mercury, they cannot use cyanide afterwards. cyanide reacts with mercury in the tailings and makes it more soluble, and therefore makes it, instead of having a regional, a localized pollution problem, we end up with a pollution that travels far distances along rivers. So this practice has to be banned. It is an obligation of the Convention for countries to ban cyanide leaching after mercury amalgamation. And as you can see from the pictures, most often it's done in a very uncontrolled manner, and there is a risk of other impacts to health and environment if cyanide is not managed properly. The last part, of course, is once the amalgam has been obtained and often combined with other amalgams from the same miners or from the village, it is refined, meaning that the gold produced is melted, and a flux is added, such as borax, for example, to remove the impurities from the metal. And this refining process is used again in every type of mining operation, either when they use only gravimetry, only mercury, or with cyanide, because it's the last step that produces gold that is quite high in concentration. So I should say on the last slide that the remaining mercury in the amalgam is released at these steps, trying to control the mercury emissions during this step is also very important. Often miners burn the amalgam on a wood fire, which gets to about 400, 600 degrees. Some mercury doesn't get vaporized in this step, and therefore it gets liberated at the refining stage. Mercury capture has to be considered in the refining stage, that often is done in cities as well, so there's a lot more exposure to the local population. Sorry, trying to move. Yeah, okay, so the main problem I cited at the beginning is that the miners are informal, and because they are informal, it's very difficult for them to access to the proper techniques and the investments needed. The second part, and what we've seen during this presentation, is that the grinding is often very poor. And poor grinding means that not all the gold will be recovered. And I have tried to schematize the process here. So if we have the top left example in not enough grinding, you can see here we consider that the black particles are gold and the white is quartz and all the other minerals of the ore. If not enough grinding is done, some of the gold is still attached to the quartz and the other ore, and therefore these parts won't be extracted, even when we apply mercury or if we apply cyanide as well. So this is bad grinding, and this is referring to the lady that was grinding manually with a piece of wood. On the other hand of the scale, miners often try to compensate that fact by grinding too much and therefore producing too fine particles. And this was reflected from the picture from Burkina-Faso, where miners were using a flour mill, grinding far too much, and therefore the gravimetric techniques used after were not efficient because the particles were too small to be separated. Or, in fact, gravimetric methods would work, but would take such a long time that the miners really don't wait for it. And then we have bad grinding altogether, where the particle size obtained differs a lot from one to the other. And here you can see that the gold particles in this example are quite small, while the quartz particle are still left quite big. Gravimetric methods will only work when all the particles are the same size. Gold is dense, it's denser than the rest of the minerals, but if the other minerals are ground too big, then they have the same weight, and therefore impossible to separate. So these are all the type of problems we have in the mining sites, why miners cannot access and extract most of the gold. One good example below is that liberated gold, where you have the exact amount of grinding that is applied, not too much, and not but the right amount, where all the particle size have the same, roughly the same size. In this case, it will be possible to do gravimetric separation, where the gold will be separated from the rest of the minerals. And this is really the key to any gold mining. And if we want to do away with mercury altogether, the grinding has to be done properly, and thereby after applying good gravimetric separation methods. So I will give you two examples of success stories in the field that have eliminated the use of mercury altogether. The first one will be on an artisanal site, so miners that are poorly trained and probably not well equipped. In this site, it was a Jeff project that I developed in 2012. We introduced, you can see on the right picture, a proper milling process. So it's called a Chilean mill. This is two wheels that are turning continuously, and you can see the sieves at the end of the exits of the mill. And these ensure that the size of the material that comes out onto the sluice is consistent, and therefore the gravimetric process will be efficient. Like in any sluice, the carpets are washed after a process, and after that the ore is further separated using a shaking table, as it's shown on the other picture. This is a very efficient tool to separate gold once the grinding has been done properly. So in this example, before the intervention on that particular site, miners were using mercury and bad grinding techniques and bad concentration. Geological studies during the project have led to the fact that the miners were extracting about 30% of the gold with their old techniques using mercury. With this equipment installed, the miners are now extracting 70 to 70% of the gold, meaning that for the same amount of ore taken out of the ground, they produce twice as much gold. And for them, it has been a great realization. And although the project has bought the first set of equipment, the miners have bought themselves another set during the project. So they were convinced enough by the new process that they were investing in the same process to replicate on their site and elsewhere. So that's really a good example of removing the use of mercury altogether and producing more gold. The second story I want to bring in is the story of a small-scale mine this time. So the Burkina was more of an artisanal site. Here we have a small-scale mine, so a bit more equipped and a bit more developed, as you can see from the pictures. But the process is very similar. Miners are grinding here in the yellow cylinder that you can see on the right picture with a Chilean mill, exactly the same process. There's a sieve at the end and sluice boxes. So there's more equipment because there's a more turnout of ore. After that, they do another gravimetric separation and extract gold directly. But the tailings, here in this case of a small-scale mine, are further extracted with cyanide after this process. Meaning the miners produce gold two ways. Once gravimetrically only, and second for the fine part with cyanide. But this side also has a very good waste management policy, and they then treat all the tailings, removing any type of metals left by precipitation, and doing after a wet treatment of the wastewater, producing no pollution to the environment. So this is a very good example of what can be done in the case of a small-scale mine. And that brings me to the tailings. Even with the best grinding and construction techniques, gravimetric methods will only extract a maximum of 70 to 80% of the gold. Some gold will remain in the tailings. And it is our view that these should be dealt with immediately during the same processing, because if miners don't deal with it, the next generation, once the ore will be depleted, will have to work on these tailings. But instead of having the ore potential, they will only be left with 20% of the original gold. So by not working on the tailings at the same time, we're just creating a cycle of poverty for the mining communities. In that said, the cyanide or any chemical leaching cannot be applied to every site. In case of artisanal miners, this cannot be done at all. The miners need to sell their tailings to an industrial partner in order to be extracted, so that miners can still get a benefit and an income from these tailings. And this is happening in a lot of sites we're working in Africa, where miners extract gold obtaining 70, 75% by gravimetric methods only, and then the tailings are further processed by an industrial partner. In case of small-scale mines, like in many places in Ecuador, Peru, miners are already using chemical leaching, and therefore this should be reinforced only when there is a strict assurance that the chemical management is satisfactory. In conclusion, to go back to the question that we had at the beginning, is mercury really needed in ASGM? The answer is clearly no. The industrial mines don't use mercury at all. It's not efficient, as we said. And it's hazardous, and it requires a lot of waste management. Mercury is a chemical compound. It cannot be destroyed once released. But for miners to move away from mercury, they need to be formalized. They need to be able to be settled in an area so that they can access the proper financing, and they can purchase the proper equipment that cannot be moved easily, which allows them to process the gold without the ore without any chemical addition. Therefore, formalization and access to finance has to be secured, and then technical training, of course. But in most of the sites we've worked with, because of the bind grinding techniques formerly used and the bad concentration techniques, applying these simple processes such as we've done in Burkina-Faso or Ecuador lead to a much increased gold recovery, and therefore it helps us convince the miners, if they do produce more gold with the same type of ore, then they will be using the new techniques. And therefore, as we said with the previous slide, the tailings have to be managed. In the case of artisanal sites, they have to be given to an external processor that does it in a controlled environment. In a case of small-scale mining, it can be done locally, but then the proper management of the chemicals needs to be ensured. And then the management of the tailings after that also needs to be taken into consideration. So that's my presentation. I think I'm within time. I'm here for questions. You can also send me any question you have by email. And then we can continue this discussion. Thank you.
Okay, thank you very much, Ludovic. As Ludovic mentioned, indeed, if any of you guys have any questions, please do not hesitate to ask them at this point. Jack, did you want to ask something?
Yes, I do. Can you hear me?
Yes, we can hear you.
Very good. Thank you, Ludovic. That was great. You know, I've been to many sites, and it's amazing how much more learning I have to do in this area. So just when you think you knew it all, someone like you comes along and is educating all of us. So thanks so much. So I have two questions. So it seems like the extent of grinding will vary with the ore and the geology of the ore. So how do you determine the ideal grinding time? Is it specific for a particular site? And then my second question is, the grinding is specific to hard rock. Is that correct? And so like alluvial gold mining that we see in other places, are they also grinding there? And so that's it.
Thanks, Jack. Good to hear you. So yes, the grinding time, it's a good question. Miners, again, especially artisanal miners, have a very limited understanding of the geology. And we have, the partnership has developed, one of our partners, not we, has developed a very good movie to explain how much grinding is necessary. So I will, if you send me an email, I will send you the link to this material. Basically, the idea is to grind a certain amount of time and then recover gold, and by gravimetric methods, and then vary the time you grind to see how much gold you recover. You will, if you go from a shorter time to longer time, increase the gold recovery, and then you will reach a point where there will be no more gold recovery, no more increase. The time this curve starts to decrease, that's when the adequate grinding is for that type of site. So this is very well explained by the video with a lot of support materials. So I will send you the link. This is one point. Second, alluvial and alluvial miners still grind the ore. In case of pure alluvial mine, it might not be so necessary, but in case of alluvial mine, gold, where you have some deposits that are not primary, the gold is still trapped into other type of minerals, and therefore it still needs to be ground. So it's, in most cases, miners apply grinding. When they do not apply grinding, of course, then that means that they recover enough gold. But in this case, I would still suggest to try this method of trying to introduce grinding to see if we can recover more gold or not. It's mostly, you know, experimentative and but leads to good results.
Yeah. Well, thank you very much. Yeah, I didn't realize alluvial, because all the alluvials I see, I don't see much grinding in the larger operations, a small scale. So, all right, thank you very much.
Mm-hmm. I mean, if miners dredging the bottom of a river, they don't need grinding. That's obvious. But if they are dredging if they are working on the riverbed, then they usually use a bit of grinding.
Okay, thank you for that. I believe, Conrad, you had a question for Ludovic?
Yes, first of all, Ludovic, again, thank you for a very insightful presentation. This is great, and I'm really glad that we'll have this for replay, because I'm sure I'd like to suggest it to others. I have a question that I think, and Pedro Fuentes has a question listed here which is close to mine, so I hope I can kill two birds with one stone and not confuse things. But in your discussion, I think you're suggesting that gravimetric separation is really the ideal solution to the use of mercury. And Pedro had also asked the question, I've been aware of borax in more primitive solutions, even just using a retort with mercury. I was wondering if there were other methods to be used in place of or in combination with gravimetric separation that would improve artisanal and small-scale gold mining.
Well, there's two, as you say, there's two prongs to your question. First of all, the use of retorts. We work in the framework of the Minamata Convention, and the Minamata Convention doesn't ban the use of mercury. It only bans the 4 worst practices I have identified. And therefore, if miners still wish to use mercury, they can, but then they have to use retorts. It's an obligation. Burning the amalgam in the open is a banned practice under the convention. So, of course, and in some sites, I mean, I've given 2 examples of where it worked very well, the gravimetric separation. But you have sites where, especially going back to what I said to Jack, if miners are dredging the silt of a river, the material there is super fine. And so, and we go back to one of the bad example of grinding, if you want, that I have shown, because in the end, the silt has been ground by natural phenomenon. And in these cases, it's very difficult to apply gravimetric methods because the silts are too fine and will take too long. In these cases, chemicals extraction has to, there's no much way around that than to use chemicals, be it mercury or cyanide. And therefore, miners could be using this under the Minamata Convention, but they have to use retorts. So that's one point. On the borax, I've mentioned this in the presentation. In any type of mining, whether you use mercury, whether you use cyanide, whether you use gravimetric methods, you will come to a point where you have to refine, and that's when the flux or borax or whatever flux is used to separate the bullion you've obtained from the impurities, so to concentrate your gold. So it's used in any case, and in case of gravimetric methods, what I didn't explain is that once you've obtained the concentrate, you have to do a smelting, and the smelting happens with a flux. So borax is used in all cases.
That's great. Thank you very much. I have even more. I have a lot more to learn than Jack does.
Okay, do we have any more questions from the audience? Yes, Maria.
Hello, this is Marie Concordel. I have a question for you about the tailings. You said that once the miners have extracted the gold, they have to sell the tailings to someone else. I was wondering how many people actually do that, because we went to visit some miners in Indonesia, and from what I recall, their tailings are just thrown away in the environment. And so, do you know how much of the tailings are actually recycled? And also, you said that once mercury has been used, you cannot use any cyanide, or I'm not sure what method you can use on tailings that are full of mercury. Can you please elaborate? Thank you.
Yep. Thank you for that. So the first question on the tailings, of course, this is the ideal. What I described is one of the situations where we had a mine nearby that were able to buy the tailings from the miners. So that the proximity of an industrial mine is an important aspect. Second, and also, I mean, as you've seen from the picture, in West Africa, most areas are dry, and therefore the tailings are contained within a very limited area, and that makes it a bit easier to control them. Miners, the industrial mines can buy the tailings because of the good grinding. They would not do it if the miners were not grounding properly, because in this case it would be too expensive for the mine to regrind and reprocess. That's two aspects. There's the case you've cited in Indonesia, and I've been to many places like this, and also in the Philippines, where the tailings, because of the topography or because of where operations happen, released directly into rivers, then this is very difficult, and this will require a much more in-depth intervention, because then in these cases you would have to move the dredges away from the rivers first in order to be able to keep the tailings. This is not a simple issue. I agree. And then the use of cyanide on mercury-contaminated tailings. As I said, this is a banned practice under the Minamata Convention. So every party of the Minamata Convention has to take steps to control that this is not happening. This is one of the most polluting practice. When you release mercury into rivers, it doesn't go into the water. Mercury is not soluble. Mercury goes to the sediments. And then from there, it can be transformed into methyl mercury and maybe taken up by the food chain. When you use cyanide on these type of tailings, the mercury is no longer only in the sediment. Mercury becomes soluble. It links to the cyanide and then becomes a water issue, and therefore polluting much wider areas. That's why this practice is banned. If miners have to work on old tailings that they didn't process in the past, and they want to use chemical extraction, then they have to first extract mercury before they can use cyanide. And that's why it's more expensive, and that's why tailings have to be managed when the main extraction is done. Don't leave the tailings to the next generations to deal with.
Okay, thank you.
Okay, thank you all for your questions. I did have one more question, Ludovic, from the audience. Could you maybe talk a bit about some of the challenges with the sustainability of these initiatives, and maybe can you overcome issues of behavioral changes, for example, in Burkina Faso?
Well, and Burkina Faso was an easy example. If you double the productivity of the miners, they will continue using new techniques. They will not revert to using techniques that leads to half of the recovery. And that's in this case, this wasn't challenging. Other sites might be more challenging, especially when miners are already using a pretty well thought about grinding methodology and concentration. Like in some cases in Mali, the grinding is actually well done, and then the concentration also, and then miners use mercury on top of that. In these cases, the gains are limited or negative, and therefore this will be challenging. And that's where the convention opens the door. I mean, the convention doesn't prevent the use of mercury, it prevents the emissions of mercury. So in these cases, the window would be more of an awareness raising for the mining communities on the risks of mercury, and making sure they don't burn in the open, and they don't release mercury during the amalgamation process. So, yeah, not all cases. I mean, every mining site is different, and climatic situation will also influence. And a lot of places where water is abundant, miners tend to do the worst things there, because they don't really care about wasting and polluting waters. New water will always come. Found that people in dry climates usually use better techniques, and therefore the transition to non-mercury techniques is a bit more difficult because they are themselves more efficient. I hope it answers a bit. I mean, I tried to give 2 examples where it works really well, but and I think one of the participants asked the question about Indonesia. I think Indonesia would be a much harder case because of the
Okay. And is it easy to get people to change ways of doing things, or is that one of the hard challenges?
Again, it's all linked about how much financial gains you have with the new techniques. If you double the outcomes, then yes, it's easy. If not, then it will be a harder and much longer process. In any case, I mean, spending time with the miners is essential. I mean, in the good case that we have seen, changes didn't happen overnight. It was a matter of 12, 24 months working with the miners to refine the techniques and to make them understand what works, what type of angle they have to use on the sluice or to capture more gold, and so on. So it is a long process and has to be accompanied by awareness raising on the chemicals used, so that there is also a push for the wider community, for the miners to stop using polluting chemicals. But this requires a long, you need to spend enough time in the mining communities to be able to ensure this is sustainable change.
Okay. Jack, I believe you had a question?
Okay. Are there any more questions?
Can I ask question, Lucy?
Yes,
Ludovic?
Go ahead, Budi.
Okay, thank you, Ludovic, for a very informative presentation. So in your presentation, you also pointed out one issue, which is formalization. But at the same time, it is also a very critical step if we want to promote like a environmental friendly techniques to the miners. But here, for example, formalization is a very big challenge because many local government sees it more as a additional burden to them. So do you have any success story on how formalization is supported fully by the government, or what will encourage the government why they have to formalize artisanal and small-scale gold miners? Thank you.
Thank you, Budi. Yeah, I mean, as I mentioned, formalization is the first step. Without formalization, miners will not invest in equipment that they can't take with them if they have to run away. So formalization is the main reason why miners use mercury in the first place. Informalization, I mean, formality. So this is a huge task, and we're working here with partners that are specialized in this this particular difficult topic. With ELL, we're working with PACT, UNITA, sister agencies, developing formalization guidelines. What we can and what we continue to communicate to the governments is that ASGM is a huge employment opportunity for rural community. Government should take action to formalize the sector, because there is very little alternative livelihood options for these people. If they were to find a proper job, most of them would have to move to the cities. And as you know, many cities in Africa and in developing countries are already overcrowded. So promoting sustainable sustainable jobs in rural areas is essential. Moreover, I mean, if you look over the gold sector, industrial gold mines around the world produce about 70% of the gold output and employ less than 50,000 people. ASGM, so artisanal and small-scale gold mining mines, produce 30% of the gold output and employ 15 million people. The employment opportunities is not with the big mines. Big mines don't employ anybody locally. They only leave behind polluted sites. So government should realize that for them it's much better to hire to promote local jobs in rural areas. This message is not so easy to pass, but that's why we're working with the partners we have linked with, who have been working in this sector for much longer than we did, in order to have more reach.
Thank you, Ludovic.
Ludovic, I have one more question. There's a large Mercury conference in Rhode Island in July. I'm sure you're probably aware of it. Will you be presenting? Will we be seeing you there?
I don't know. You should ask my boss about this. Yes, the plan is I've submitted an abstract and I'm planning to attend. But we will talk mostly about Minamata initial assessments. What are the needs of countries with the Minamata Convention? My abstract is more about mercury in general, but I'm happy I will attend all the sessions on the ASGM that I can.
That's great. All right, I'll see you there.
Hopefully.
Okay, if there are no more questions, I think we're going to end this info session. Okay. Please don't forget that if you do have any more questions, either for Ludovic or anybody else who spoke today, please do not hesitate to contact Ludovic directly. You can see his email address appearing on the screen at the moment. The recording of this info session will be present on the GAP website in a few days, so don't hesitate to go see that if you want to see it again. And we hope that you will be joining us for the next info session on Thursday, March 23rd at the same time, so at 8 a.m. New York time. And this time it'll be on approaches to measuring health impacts at toxic waste sites, and it'll be presented by Jack Caravanos, who you've actually just heard. And the info connection will be the same as for all these past info sessions. Thank you very much for your attention. Bye, everybody.